The general reflection property. Okay, let's begin with slide 1. Welcome! In our continued exploration of definite integrals, we're going to delve into a really useful technique for simplifying integrals, something called the general reflection property. Now, remember that definite integrals represent the area under a curve. Sometimes, directly calculating that area can be quite challenging. That's where properties like this one come in handy. These properties allow us to rewrite the integral, to change its appearance, without actually changing the value of the area it represents. Think of it like rearranging the terms in an algebraic equation. You're not changing the answer, just how you write it. This particular property, the general reflection property, is often labeled as property P subscript 3. You might see that notation later. It's a powerful tool, and its foundation lies in a geometric idea, reflecting a function. Imagine you have a function graphed on a coordinate plane. This property is based on the idea of reflecting that graph across the midpoint of the interval we're integrating over. It might sound a bit abstract now, but we'll see how it works in practice. In more practical terms, what this property lets us do is substitute the variable x within the integral with a new expression involving the upper and lower limits of integration. Specifically, we replace x with a linear combination of a and b, where a and b are the lower and upper limits of our integral. This substitution often leads to simplification. Either the integrand, which is the function we're integrating, becomes easier to work with, or terms cancel out, making the integration process much smoother. We'll see exactly how this works in the following slides, but this slide serves as a good introduction to the core idea behind the general reflection property. The mathematical statement. Okay, so let's move on to slide 2, where we state the general reflection property mathematically. As we discussed on the previous slide, this property is a powerful tool for manipulating definite integrals. Now, we're going to see exactly what it states. Here, we have the general reflection property. It states that for any continuous function, and remember, continuity is important for definite integrals, which we're calling f of x, defined on a closed interval from a to b, indicated by square brackets a comma b, the integral of f of x with respect to x from a to b is equal to the integral of f of a plus b minus x with respect to x, also from a to b. Let me break that down a little further. The integral symbol, followed by f of x, dx, represents the definite integral we're trying to evaluate. The limits of integration, a and b, define the interval over which we're integrating. Now, the core of the property is this replacement. Instead of integrating f of x, we integrate f of a plus b minus x. This means wherever you see an x inside the function, f, you replace it with the expression a plus b minus x. Crucially, notice that the limits of integration, a and b, stay the same. We are not changing the interval over which we are integrating, only the function inside the integral. This property essentially says that the area under the curve of f of x between a and b is the same as the area under the curve of this reflected function, f of a plus b minus x, also between a and b. We'll see how this works in practice on the following slides, particularly when we introduce the 2i method. But for now, it's important to understand this mathematical statement as the foundation for applying the property. Remember this formula, as it's the key to unlocking some tricky integrals. Breaking down the property. Okay, so now we're going to break down how this general reflection property actually works. Remember from the previous slides, we introduced this property, often called property P sub 3, as a way to rewrite definite integrals. This slide outlines the key steps to really grasp what's going on. Let's start with the first step, identify the limits. This is pretty straightforward. Before you do anything else, you need to clearly identify what your lower limit of integration is, which we denote as a, and your upper limit of integration, denoted as b. These are the starting and ending points of the area we're calculating. Keep these numbers firmly in mind, as they're crucial for the next step. Next, we have the transformation. This is where the core of the property comes into play. Instead of integrating the original function, f of x, we're going to integrate a modified function, f of a plus b minus x. What this means is that wherever you see an x inside the function f, you replace it with the expression a plus b minus x. It might look a little strange at first, but it's a simple substitution. Think of it like changing variables. Now, a really important point: consistency of limits. Don't fall into the trap of thinking you need to change the limits of integration when you make this substitution. The limits remain exactly the same, a and b. We do not swap them, we do not change their values. They stay put. This is vital. Finally, equality of value. This is the conceptual heart of the property. What the property is telling us is that the area under the curve of the original function, f of x from a to b, is exactly the same as the area under the curve of the transformed function, f of a plus b minus x, also from a to b. It's as if we've reflected the function across a central point and the area hasn't changed. Keep in mind that we'll be seeing how this property is actually used to solve integrals in the following slides, particularly with the 2i method. But understanding these steps, identifying the limits, performing the transformation, maintaining consistent limits, and recognizing the equality of areas is fundamental to applying the property correctly. Application strategy: the $2 method. Okay, so we've established what the general reflection property is, property P3, as we've been calling it. Now, let's talk about how to actually use it to solve integrals. As you can see on this slide, the general reflection property is very rarely used by itself. It's much more powerful when combined with a clever technique we call the addition method, or, more informally, the 2i method. The 2i simply stands for 2 times the integral. We'll see why in a moment. Let's break down the steps of this 2i method. Step 1. Assign a variable. We start by assigning the integral we want to solve to a variable. It's common to use I for integral. So, we write I equals the definite integral from a to b of f of x dx. Remember, dx simply indicates that we are integrating with respect to the variable x. Step 2. Apply property P3. This is where we bring in the reflection property we just learned. We rewrite the same integral, I, but this time using the reflection property. That means we replace x within the function f of x with a plus b minus x. So we now have I equals the definite integral from a to b of f of a plus b minus x dx. Notice that the limits of integration, a and b, remain unchanged. Step 3. Add the 2 equations. This is the core of the 2i method. We now have 2 expressions for I. We add them together. This gives us 2i equals the definite integral from a to b of the quantity f of x plus f of a plus b minus x dx. Essentially, we're adding the original integral to its reflected counterpart. Step 4. Simplify and solve. This is where the magic usually happens. When you add f of x and f of a plus b minus x, the result often simplifies dramatically. It frequently collapses into a much simpler expression, perhaps a constant or a function that's easy to integrate. We then integrate this simplified expression with respect to x, and finally, because we multiplied the original integral by 2 in step 3, we must divide the result by 2 to isolate I and find the actual value of the integral. Now, keep in mind that we'll see this method in action with some examples on the next slides. We'll work through some specific integrals to really solidify how this 2i method works. But this slide lays out the general strategy. It's a powerful technique, and once you get the hang of it, you'll find it makes solving certain types of definite integrals much easier. Worked example 1, trigonometric simplification. Okay, let's tackle this example. As we discussed on the previous slides, we're going to use the general reflection property, or property P3, to evaluate this definite integral. Here's the integral we need to solve. The integral from pi over 6 to pi over 3 of sine of x divided by sine of x plus cosine of x, with respect to x. Step 1. The first thing we always do when using the 2i method is to assign our integral to a variable. In this case, we'll call it I. So, we write I equals the integral from pi over 6 to pi over 3 of sine of x divided by sine of x plus cosine of x. With respect to x, we'll label this as equation 1, just for easy reference. Step 2, now we need to identify our limits of integration and apply the reflection property. Our lower limit, is pi over 6, and our upper limit, b, is pi over 3. It's crucial to get these right. Next, we calculate the sum of the limits, a plus b, which is pi over 6 plus pi over 3. This simplifies to pi over 2. Remember, we're going to substitute a plus bx for x in our original integral. So we replace x with pi over 2 minus x. This gives us a new integral. The integral from pi over 6 to pi over 3 of sine of pi over 2 minus x, divided by sine of pi over 2 minus x, plus cosine of pi over 2 minus x. With respect to x, notice that the limits of integration, pi over 6 and pi over 3, remain unchanged. Step 3, now comes a key step where we use our trigonometric identities. Recall that the sine of pi over 2 minus x is equal to the cosine of x, and the cosine of pi over 2 minus x is equal to the sine of x. Applying these identities to our integral, we get the integral from pi over 6 to pi over 3 of cosine of x divided by cosine of x plus sine of x. With respect to x, let's label this as equation 2. Step 4, this is where the magic happens. We add equation 1 and equation 2 together. So, 2I equals the integral from pi over 6 to pi over 3 of sine of x divided by sine of x plus cosine of x, plus cosine of x divided by cosine of x plus sine of x. With respect to x, if you look closely, the denominators are the same, so we can combine the fractions. This simplifies to the integral from pi over 6 to pi over 3 of sine of x plus cosine of x, divided by sine of x plus cosine of x. With respect to x, the sine of x plus cosine of x terms cancel out, leaving us with just the integral of 1 with respect to x, from pi over 6 to pi over 3. Step 5, finally, we integrate and solve for I. The integral of 1 with respect to x is simply x. So, 2I equals x evaluated from pi over 6 to pi over 3. This means 2I equals pi over 3 minus pi over 6, which simplifies to pi over 6. To find I, we divide both sides by 2, giving us I equals pi over 12. And there we have it. We've successfully evaluated the integral using the general reflection property and the 2I method. Remember, this technique is particularly useful when the integrand has a nice symmetry that we can exploit with this reflection. We'll see more examples and also discuss common mistakes to avoid on the next slides. Worked example 2. Algebraic reflection. Okay, let's move on to our second worked example. This one demonstrates how the general reflection property, or property P3 as we've been calling it, can be applied to an integral involving algebraic functions. Here on the slide, we're asked to evaluate the definite integral of square root of x minus 2, all divided by square root of x minus 2 plus square root of 4 minus x, with the limits of integration being from 2 to 4. Step 1, as we discussed with the previous example, the first thing we do is assign our integral to a variable. In this case, we'll call it I. So, we write I equals the integral from 2 to 4 of square root of x minus 2 divided by square root of x minus 2 plus square root of 4 minus x, and we label this as equation 1. This is just a standard practice to keep things organized. Step 2, now we apply property P3, the general reflection property. Remember, this property states that the integral from a to b of f of x dx is equal to the integral from a to b of f of a plus b minus x dx. In our case, the lower limit, a, is 2, and the upper limit, b, is 4. Therefore, a plus b equals 2 plus 4, which is 6. Now the crucial part, we replace every instance of x within our integrand, that's the function we're integrating, with 6 minus x. So, wherever we see x, we substitute 6 minus x. Let's carefully apply this substitution. We get square root of 6 minus x minus 2 all over square root of 6 minus x minus 2 plus square root of 4 minus 6 minus x. Simplifying inside the square roots, we have square root of 4 minus x in the numerator and square root of x minus 2 in the denominator. This new integral, with the reflected function, is also equal to I, and we label it as equation 2. Step 3, this is where the magic happens. We now add equation 1 and equation 2 together. When we do that, we get 2i equals the integral from 2 to 4 of the sum of the two integrands. So, we have 2i equals the integral from 2 to 4 of square root of x minus 2 divided by square root of x minus 2 plus square root of 4 minus x plus square root of 4 minus x divided by square root of x minus 2 plus square root of 4 minus x. Notice what happens when we add those two fractions. The denominators are identical. This allows us to combine the numerators, giving us 2i equals the integral from 2 to 4 of square root of x minus 2 plus square root of 4 minus x, all divided by square root of x minus 2 plus square root of 4 minus x. And beautifully, the entire fraction simplifies to 1 because the numerator and denominator are the same. So, we're left with 2i equals the integral from 2 to 4 of 1 dx. Step 4, now the integration is straightforward. The integral of 1 with respect to x is simply x, so 2i equals x evaluated from 2 to 4. This means we calculate the value of x at the upper limit, 4, and subtract the value of x at the lower limit, 2. This gives us 2i equals 4 minus 2, which equals 2. Finally, we divide both sides by 2 to solve for I, and we find that I equals 1. And there you have it. We've successfully evaluated the integral using the general reflection property and the 2i method. Remember, this technique is particularly useful when the integrand has a symmetric form, as we saw in both of our examples. Now, let's move on to the next slide, where we'll discuss some common mistakes to avoid when applying this property. Common mistakes to avoid. Mistake 1, changing the limits. A very frequent error is accidentally altering the limits of integration, that is, the values a and b that define the interval over which we're integrating. Remember, the whole point of the reflection property is to transform the function inside the integral, not to change where we're integrating from n to. The limits a and b stay exactly the same before and after applying the property. Don't swap them, don't add or subtract anything from them, keep them consistent. Mistake 2, incorrect sum of limits. This one's about basic arithmetic, but it trips people up. When you need to calculate a plus b, make sure you do it correctly. A small calculation error here can throw off the entire substitution. For instance, the slide gives an example with trigonometric integrals. If a is pi over 6 and b is pi over 3, then a plus b is pi over 2, not 2 pi over 9. Double-check your addition, especially when dealing with fractions or trigonometric values. Mistake 3, forging the 2i step. Now, this is a big one. Students sometimes apply the reflection property, get a new integral, and then try to solve that directly. But remember, the real power of this property comes from using the 2i method, the addition method we discussed. You need to write down the original integral, apply the reflection property to get a second expression for the same integral, and then add those two equations together. That addition is what usually simplifies the integrand and makes it solvable. Don't skip that crucial step. Mistake 4, sign errors in substitution. Finally, when you're replacing x with a plus bx inside the function, be extremely careful with your signs. It's easy to make a mistake, especially when you have square roots or trigonometric functions involved. A misplaced minus sign can completely change the problem. Take your time and double-check your algebra to ensure you've correctly substituted and simplified the expression. Okay, so we've learned how to use the general reflection property, also known as property P sub 3, to tackle some tricky integrals. Now, let's look at some common pitfalls students often encounter. This slide, slide 7, is all about avoiding those mistakes. So, keep these common mistakes in mind as you practice. We'll now move on to the final slide, where we'll recap the key takeaways from this entire lesson. Key takeaways. Okay, let's recap everything we've learned about the general reflection property. This is a crucial slide to solidify your understanding before we move on to more complex integration techniques. First, let's look at the formula. We have the definite integral of a function f of x, with respect to x, from a lower limit of a to an upper limit of b. This is equal to the definite integral of f of a plus b minus x, with respect to x, also from a to b. Remember, this isn't about solving the integral directly, but about rewriting it in an equivalent form. Now, purpose. Why do we bother with this seemingly strange transformation? The main reason is to simplify complex integrands. Often, the function f of a plus b minus x will combine with the original f of x in a way that makes the integral much easier to evaluate. It essentially creates a symmetric counterpart that allows for cancellation or simplification. Let's talk about the strategy. As we discussed in the previous slides, the most powerful way to utilize this property is through what we call the 2i method. Here, we first assign the original integral to a variable. Then, we apply the reflection property to rewrite the same integral. Still as I, finally, we add these two equations together. This gives us 2 times I, which is equal to the definite integral from a to b of the sum of f of x and f of a plus b minus x. This addition is the key step. It's where the simplification usually happens. Finally, geometric meaning. It's helpful to visualize what's happening. This property essentially states that the area under the curve of f of x from a to b is identical to the area under the curve of its reflection across the vertical line, x equals a plus b divided by 2. Think of it like folding the graph along that vertical line. The areas will match up perfectly. This is why the value of the integral remains unchanged, even though we've altered the function inside the integral. So, to reiterate, remember the formula, understand the purpose of simplification, master the 2i method, and keep the geometric interpretation in mind. This will give you a solid foundation for tackling more challenging definite integrals. Are there any parts of this slide you'd like me to explain in more detail?